Okay, so now we have to use the difference quotient to find the value given by the function y equals x squared minus x plus 3. So I told you the difference quotient's main goal was to find slopes of things that were not lines. Right? So like right here's a parabola. It's an x squared function. So the difference quotient allows us to find the slope of it where we couldn't do that any other way. So this is the main reason that we are using this difference quotient. So just a reminder, right here it is. It's f of x plus h minus f of x all over h. So what we do is we plug in x plus h for our x value, and then we're going to subtract the original function and then divide all that by h. Okay, so let's do that. So first we're going to plug in x plus h. So that's going to give me, instead of x, it's x plus h squared minus x plus h plus 3. So that is f of x plus h. Now that I'm going to subtract, because there's a built-in subtraction, and I'm subtracting all of f of x. So f of x is x squared minus x plus 3. And again, we're subtracting all of that. And then this is all going to be divided by h. So the green is f of x plus h. Then the subtraction comes from the formula. The blue is f of x, and then we're going to divide that by h. Now we have to simplify. So I've got x plus h squared, which means we're going to distribute that. X plus h times x plus h minus, now then all this is being subtracted, so I'm going to distribute a -1 there. So this becomes minus x minus h plus 3. And then again, all of this is being subtracted, so I'm going to think about distributing a -1 throughout the blue. So that's going to become negative x squared plus x minus 3. And then that's all over h. Now I need to distribute like I said I was going to do. I don't know why I didn't do it. I just said I was going to. I guess so you could see it at the beginning. So x times x is x squared. X times h is hx. H times x is hx. So I've got 2 hx's. So that's going to be plus 2hx. And then h times h is h squared. Then bringing down everything else, minus x minus h plus 3 minus x squared plus x minus 3 all over h. And now then we want to look for like terms in the numerator. So I have an x squared minus an x squared. So those are gone. I have a negative x plus an x. So those are gone. I have a plus 3 minus 3. So those are gone. Okay, there's going to be 3 pairs of terms that cancel each other out on 99% of these problems. Okay, so once you find 3 of them, you've probably done it correctly. 3 sets that cancel each other out. So now what's left? I have an h squared plus 2hx minus h all over h. Okay, well now every term in the numerator has an h. So I have a GCF of h. So I want to factor that h out. So that's going to be h times h plus 2x minus 1 all over h. And now I can cancel out that h in the numerator and denominator, which leaves me with h plus 2x minus 1. Okay, so again, I'm just plugging directly into the difference quotient formula. So first I need to find f of x plus h. So I'm going to substitute in x plus h for x. So that becomes 3 radical x plus h. Then the subtraction comes from the formula. And now I'm just going to subtract f of x, which is 3 radical x. And this is all going to be over h. So for everything that we've done right now, this is fine. Okay, what we have here, this would be the final answer. The problem is when you get to calculus, you're going to start taking limits of things like this. Okay, well that is...
No, that's for me,
Oh, well that is kind of what happens in Precal and calculus. So if you take a limit, you're saying as something gets very, very close to a number. So, for instance, our big problem here is we could divide by 0, right? That could be a problem. If you'll remember when we started talking about rates of change, and I think I did that in here, how a radar gun works on a cop car, that it shoots 2 radar beams as fast as they can, back to back. So what we're looking at, this H is the time between those 2 points. We want that to basically be 0. We want it to be as close to 0 as it can be, because that gives us the closest thing to the instantaneous rate of change. Does everybody follow that? We want this to be 0. So what we do when we start taking limits is, well, the limit as H approaches 0, we would just plug in 0 for H. Well, that would give me a problem because I can't divide by 0. So this would be in what's called indeterminate form, where we can't divide by 0. Now, you don't need to know all that stuff right now for what we're doing, but I wanted to give you context for why we're fixing to do what we're going to do with this problem. So we would not be able to work this problem because we would be dividing by 0. So we need to get this in a different form where we are not going to be dividing by 0. And so the way we're going to do that is we're going to rationalize the numerator instead of rationalizing the denominator. And we're going to see what that gives us. So we notice in the numerator, both of those terms have a 3. So we GCF a 3. So that's going to leave me with the square root of x plus h minus the square root of x. This is all going to be over h. Now, if we want to rationalize this, we want really our radicals to cancel each other out. And so we've worked problems like this in the past. 2 things being subtracted here, we want them to cancel each other out. We want to multiply by the conjugate, which means we're going to multiply by the same thing but put the opposite sign between them. So it's the square root of x plus h plus the square root of x. And so that will cancel out the radicals in the numerator. To keep this balanced, I must also multiply by the same thing in the denominator. Square root of x plus h plus square root of x. Okay, so what happens when I multiply in the numerator? Square root of x plus h times square root of x plus h is going to give me just x plus h, because those radicals will cancel each other out, multiplying a radical by a radical that has the exact same thing underneath them. Well, they don't... Okay. Let me just make sure we understand what's happening. So square root of x plus h times square root of x plus h. You don't have to write this down. I just want you to think. That's going to be the square root of what goes underneath. X plus h times x plus h. Well, what is x plus h times x plus h? We could rewrite that as x plus h squared, because it's being multiplied by itself. And when you square root something that's being squared, that cancels each other out. Okay? I thought I need to show you that because I know you're not very good at radical math. So you're actually multiplying the things underneath the radicals. But when the 2 things underneath the radical are the same, then that cancels the radical out, is all that really does. So that's going to leave me with an x plus h. Now watch what happens when we multiply outside and inside. Remember when you multiply conjugates. Square root of x plus h times x. That's going to be the square root of x times x plus h. And then we want to multiply negative square root of x times the square root of x plus h. That's going to give me negative square root of x times x plus h. And so what happens with those 2 terms? They cancel because they are the same thing underneath, but one's positive and one is negative. And then lastly, we're going to do the square root of x, or the negative square root of x times the positive square root of x. That's going to just give negative x. And this is going to be over h times the square root of x plus h plus the square root of x. Now we look in the numerator to see if we get anything that will cancel. X minus x is 0, so I've just got 3 times h over h times the square root of x plus h plus the square root of x. Now look, I have an h factored in the denominator and an h being multiplied in the numerator, so those cancel each other out. And so that leaves me with just 3 over the square root of x plus h plus the square root of x. And so now if we were taking a limit where h was basically 0, the distance between the two beams was basically 0, well now then I don't have a divide by 0 error. I have a square root of x plus h plus square root of x. So I have fixed this where I can take a limit of it in calculus. Okay, who's ready to have some fun? Yeah. Okay, so now then we've got to find f of x plus h minus f of x all over h. But this time, my function is a fraction. So we're going to have this fraction plugged into a formula that has a fraction. So you're going to have to be very particular about how you write these stuff. Make sure you're being very, very careful. Okay, so we're going to first find f of x plus h. That's where I plug in x plus h to my function. So that's going to give me 3 over x plus h for my f of x plus h. Now then there's a subtraction from f of x. And now I plug in my f of x, which is just 3 over x. And then this is all divided by h. So you see how I have a fraction in the numerator being subtracted by another fraction in the numerator, and then that's divided by h here. So what we want to do is we want to focus on the numerator here, which is f of x plus h minus f of x. I'm subtracting two fractions, so I need to get a common denominator. So the common denominator of x plus h and x we can get by multiplying each thing by the other denominator. So if I multiply, green doesn't show up very well on my end. I think it's fine on yours. Let's do blue. I want to multiply this first fraction by x over x. And I want to multiply the second fraction by x plus h over x plus h. Because now that gives me a common denominator of x times x plus h. So let's go ahead and write that out. So the denominator is going to be x times x plus h. Now we look in the numerator. X times 3 is 3x. And then I have a negative 3 times x will be negative 3x. And then a negative 3 times h is going to be negative 3h. So again, this is just the numerator. And so remember, all of this is over h that's in the denominator. Okay, so looking in the numerator of the numerator, I've got 3x minus 3x minus 3h. Well, 3x minus 3x cancels. That leaves me with a negative 3h over x times x plus h. And then this is all over that h from my original formula. Okay, so some of you may know a slick move of how to simplify this. You know exactly how to make this into a fraction. I used to struggle with this more than anything. When I had fractions inside fractions, I would get so lost in all the... because they used to tell us, okay, so you just put the h on bottom, but I didn't ever understand that. So what I came up with that helps me keep everything the way it's supposed to be, This here is the built-in fraction bar, which is here, which is here. So this just kind of got manufactured because of what my function was. But this is the big fraction bar. So this is the denominator of that. So I always put that denominator over 1. And that helps me see, hey, here's my big fraction. And now what I have is a fraction divided by a fraction. And then I would go back to 5th grade, where I learned how to deal with fractions divided by fractions. So I literally would write this down like a 5th grade problem. Negative 3h over x times x plus h is going to be divided by h over 1. So what did we do when we first learned about dividing fractions? Well, we learned we can't divide them. So instead we would multiply by the reciprocal. So I changed division to multiplication and I flipped the second fraction. Now I can perform this multiplication. So I'm looking to cross reduce. I have an h and an h that will reduce out. That leaves me with negative 3 times 1 is negative 3 over x times x plus h in the denominator. Okay, so our 6 basic parent functions, we want to plot the points to the graph. We want to identify the domain and range. We want to state whether this graph is a function or not, and then identify the intervals over which the function is increasing or decreasing. Okay, so our first function is the linear function, which is y equals x. So with all of our functions, we want to have 5 critical points, okay, besides the rational function, but we're not going to get into that one yet. So for all these functions we're going to learn about, you need 5 critical points, which means I need 5 x values. Whenever I'm left to choose my x values, I always want to choose negative 2, negative 1, 0, 1, and 2. That way I can see what's happening on the left side of the graph, what the y-intercept is, and then we want to find out what's happening on the right side of the graph. So this does all of those things for us. So now we just simply plug in. If I plug in negative 2 for x, the y value is negative 2. If I plug in negative 1 for x, the y value is negative 1. If I plug in 0 for x, the y value is 0. Plug in 1 for x, you get 1 for y. 2 for x, 2 for y. Everybody see where that's coming from? Plugging into the function. Now graph those points. So negative 2, negative 2, negative 1, negative 1, 0, 0, 1, 1, 2, 2. So my parent function looks like a line. Now you know a lot about lines because you spend all of Algebra 1 looking at graphing a line. So you could look at this, you could identify the slope is 1, the y-intercept is 0, and you know a different way to graph this line. Okay, but for this, we want to kind of retrain our mind to think about plugging in these x values, finding these y values, because that's the way we want to work all of these problems. And you'll see more about that later on. So now, what's the domain? So again, I'm imagining myself walking along the x-axis. When I start walking, my graph exists already because of the arrow. So I have x values. When do I stop having x values? Well, I don't. The x values continue forever to the right. So the domain would be negative infinity to positive infinity. And now we do the same with the range. Imagine myself walking along the y-axis, so I'm down here. The lowest y value, well, it continues to go down, so it's negative infinity. The highest y value, well, it continues to increase, so it goes to positive infinity. Okay, now where is my function increasing? Where is it decreasing? Where is it constant? So again, we're imagining a timeline. I'm going from left to right. When I come upon this graph, the graph is going up from the very beginning. And as I continue to walk, the graph continues to increase, continues to go up. Therefore, this graph is always increasing. So it's increasing from negative infinity to positive infinity. It's never decreasing. It's never constant. The last thing we want to know is this a function? Okay, well, does it pass the vertical line test? Well, if I drew a vertical line, any vertical line, it would only touch the graph one time. So this is indeed a function. Okay, my next parent function is called the square function. Y equals x squared. Okay, so you have spent some time graphing this in Algebra 2, but maybe not as much time as you needed to. So we're going to focus on it some more here. So again, I need some points to graph this line. I would always like to find out what's happening on the left, on the right, and the y-intercept. So I'm going to plug in -2, -1, 0, 1, and 2. If I plug in -2, -2 squared gives 4. If I plug in -1, -1 squared gives 1. 0 squared, 0. 1 squared, 1. 2 squared, 4. So now I graph those 4 points to get a general shape of the graph. -2, 4. -1, -1, 0, 0, 1, 1, 2, 4. Now when we graph a square function, which is a parabola shape, we have to make sure that we make that bottom portion look like a U and not a V. Okay, because it is rounded out at the bottom. So if that wants to be your point of emphasis there, make sure for a square you have that rounded. Not like rounded like a U, not like a V. So now we want to identify the domain and the range. So first, what are the possible x values? Well, the lowest x value, well, the graph continues to go left. So the lowest x value is -infinity. Their graph is going, and then it continues to go to the right. So the domain would be from -infinity to positive infinity. We can plug in any x values and find a y value. Next, we want to identify the range, which is the list of possible y values. What's the lowest y value this graph takes on? Well, the graph is not happening down here, and there are no arrows putting me in the negative direction. So there are no negative y's. The lowest y value occurs here at 0. So the lowest value of the range is 0, and it's included, so we put a bracket. Now the highest y value. Well, this graph continues to climb upwards, upwards, upwards forever. So the highest y value is positive infinity. Next, we want to tell where is my function decreasing and increasing. Okay, so I'm imagining myself walking along a timeline along the x-axis. When I first see this graph, as I'm walking along, the graph is decreasing. It's coming down. So from -infinity up until 0, the graph is going down. So the function is decreasing from -infinity till 0. Okay, where's my function increasing? Well, it was decreasing all through here. Then once we get to 0 and start walking to the right, the graph is now going up in value. It's increasing, and it does that forever. So this graph is increasing from from 0 until positive infinity. And then lastly, is this a function? So think, would it pass the vertical line test? If you drew vertical lines, all of them would only touch the graph one time. Therefore, this does pass the vertical line test, so it is a function. Okay, our next parent function is the absolute value function. Okay, so this is the function y equals the absolute value of x. So when I graph this function, I want to see what happens on the left side, what the y-intercept is, and what happens on the right side. So I want to plug in -2, -1, 0, 1, and 2. That's always what I want to plug in. If I plug in -2, the absolute value of -2 is +2. So when I plug in a -2, the y value is +2. When I plug in -1, the absolute value of -1 is +1. The absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. Okay, so now I'm going to graph these points. So -2, 2, -1, 1, 0, 0, 1, 1, 2, 2.
Is that a B?
Yes.
How do you?
The absolute value function is a V shape. That's why it's so important to know the difference between the two. Because this one is essentially two lines. On the left side, we have the line y equals -x, which means if I plug in a negative x value, then negative x makes that become positive. So this is the line y equals -x. On the right side, you have the line y equals x, where whatever x you plug in, that's what you get out for y. So you see that's what's happening here. So these are two lines that are intersecting. Hopefully you can draw your lines to look a little bit better than mine. Mine looks lopsided. Okay, but I'm not a very good drawer. And I don't think it helps that they just handmade this graph either. I think that also hurts.
Everything's crooked.
Yep, I agree. So, what is the domain of this graph? Okay, what x values could we plug in?
All of them.
All of them. So from -infinity to +infinity is my domain. Now the range is what y values does this give?
0 and greater.
Yes, the lowest possible y value happens at 0, and then it goes up forever. 0 is included, so it should be in a bracket up to +infinity. Next, where is my graph decreasing? So as I walk along a timeline on the x-axis, when I first see this graph, it is going down. So this graph is decreasing from -infinity up until 0, and then it stops decreasing. So it's decreasing from -infinity until 0, and then the graph starts to go up. So it is increasing from 0 forever in the right direction. So it's increasing from 0 to infinity. Is this a function? Yes, it is, because it passes the vertical line test.
Why don't we put brackets on the decreasing and increasing? We don't want to do that.
You never put brackets on increasing or decreasing. Because if you put brackets, look at 0. At 0, is this graph increasing? Is it decreasing? No, it's what's called a critical point, or a point of concavity, where the graph is changing its direction. So at the point that it changes, it can't be doing both things. A graph can't increase and decrease at the same time. So we leave it out. It does neither. It's not constant either. Right? A little confusing. So we never include for increasing or decreasing. Now, if you are using the My Math Lab program, it has some glitch, and it makes you include them. If you remember when we read at the very beginning, they said on the program you're going to have to put a bracket instead of a parenthesis. So if you take this at Northeast, there will be times you put a bracket, but it doesn't really, that's not right. Okay?
For it to be constant, you have to have 2 points. So then you just have At one point at 0, 0, there's no way it happens.
Okay, next we're taking the square root of x as our parent function. The square root of x. So I need some x values to plug in. So what x values do I want to plug in? Well, I'd like to plug in -2, -1, 0, 1, and 2. I wouldn't write those down though. Because why not? What happens when I take the square root of -2?
We get I square root of 2.
Well, we get an imaginary number, which is, how do you graph an imaginary number? You can't, okay? Graphs only happen in the real number system for now.
So this one just starts at 0.
So -2 and -1 are not valid x values. So while I would like to plug those in, they don't make sense to plug in for a square root. So I can plug in whatever x values I want. So what things would I like to take a square root of? 4 would be a good one. Yeah, perfect squares, absolutely. So my x values here, I've got to have 5 of them, I told you, for our parent functions. So I'm going to pick the first 5 perfect squares. 0, 1, 4, 9, and 16. Now we plug them in. What is the square root of 0? It's 0. What's the square root of 1? 1. What's the square root of 4? 2. The square root of 9. 3. The square root of 16. 4. So those are my 5 critical points. So do you understand why I chose different x's this time? Because I'm taking square roots of these. So this is what I'm telling you. You're either going to have to memorize these or you're going to have to be able to think for yourself how we came up with these x values. It's up to you. For me, I hated memorizing, so I thought through it every time. But some of you may just want to memorize it, and that's fine. I don't care how you remember it, as long as you can get there. Now, 0, 0, 1, 1, 4 and 2, 9 and 3, and then 16 and 4. It's not going to fit on our graph here, but I can make it work because I've got unlimited space. Now, when I graph this, it looks something like that. So what is the graph of the square root of x, really? Well, it's really half of a parabola turned on its side, right? That's how it works. If you think about your parabola, what are our critical points? 1, 1, 2, 4, 3, 9. You see how they're just swapped their value. 1, 1, 2, 4, 3, 9, 4, 16. So it's going in the other direction. So a square root of x is it has very similar characteristics to a parabola because it's the inverse of a parabola. Anyways, so this is my graph. This is what it looks like. So what is the domain? So what all x values work for this graph? Well, we couldn't plug in anything negative, right, because that was bad. So the first x value that worked was at 0. And 0 is included, so the domain starts at 0. And then what is the greatest x value? Well, we can take the square root of any positive number. So the greatest x value is positive infinity. The graph goes forever in the right direction. Next, the range. What are the list of y values? Well, the lowest y value, it doesn't happen down here. There are no negative y's. The first y value starts here at 0, so my range is at 0. And then how high does this graph go? Well, it's not going up as quickly as it's going to the right, but it is still always going up forever. So the greatest y value is also positive infinity. Okay, so again, imagine we're on a timeline, and we want to know what are our x values doing. So as I move from left to right, this is increasing, right? And it's always increasing. So this graph would be increasing from 0 to infinity. It would never decrease. It's never constant. Is this a function? Does it pass the vertical line test? Yes, it does. So again, in order to graph it, I want to know what's happening on the left side of the graph, the right side of the graph, and the y-intercept. So the x values I'm going to choose are -2, -1, 0, 1, and 2. If I plug in -2 and cube that, that's going to be -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. So now with those 5 critical points, I'm going to graph them. So I go to -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. Okay, so the graph of a cube function that's not very good. That's better. Looks something like that.
It's a parabola, but half of it is upside down.
So the domain is the list of x values. So I start on the left. The graph keeps going left forever. So the smallest x value is -infinity. Now the greatest x value is +infinity. So my domain is from -infinity to +infinity. The range is the y values. So its lowest y value is -infinity. Its highest y value is +infinity. So the range would also be from -infinity to +infinity. Okay, now we got to see, where's the graph increasing, decreasing, or constant? Well, as I happen upon the graph, moving from left to right, the graph is going up. And the graph's still going up and still going up and still going up. So the graph is always increasing. So it's increasing on the interval from -infinity to infinity, which means it's never constant and it's never decreasing. And then again, this passes the vertical line test, so it is a function. Okay, the next one is the cube root function. So again, I'm allowed to choose whatever x's I want to. I'm going to get a cube root. So what's the cube root of -2? Like, that'd be the first number I'd want to plug in. Well, it's going to be ugly. Okay, that's not a number that we like. So if you'll remember when we had the square root function, our x values we plugged in were things that were perfect squares. 0, 1, 4, 9, 16. So now we're going to plug in perfect cubes to the cube root function because it gives us nice points to work with. So unlike perfect squares, perfect cubes can be negative, because think about what a cube root means. If I multiply something 3 times to get that number, well, if you multiply 3 negatives, you get a negative number. So cube roots you can take cube roots of negative numbers. So my cube roots are 0, 1, and 8. So to see what happens on the negative side, we're going to plug in -8. Then -1, 0, 1, and 8. So you'll see it's the y values from the cube function are what we're plugging in for x to the cube root function. So what's the cube root of -8? That is -2. The cube root of -1 is -1. Cube root of 0 is 0. 1 is 1. 8 is 2. And now we graph that. So I go to -8, -2, plot a point. Then -1, -1, 0, 0, 1, 1, and then 8, 2. And so my cube root function looks like this. So again, we're going to find the domain. That's the list of x values. So I've got negative infinity to infinity. It goes forever in the left and right direction. The range is negative infinity to positive infinity. It goes up and down in both directions forever. And again, increasing or decreasing. If I walk left to right, the graph is going up. Slowly, but it is going up. And it's still going up, and it's still going up, and it's still going up. So this graph is always increasing. So it's increasing from negative infinity to positive infinity. And it again passes the vertical line test. So it is also a function. Okay, so again, we're going to look at a couple of special linear equations. So just like we had before, when we were going over point slope form, slope intercept form, we had two special cases. That is when I have a horizontal line and a vertical line. So right here, if I look at the graph of y equals 4, that's where my y values are always 4. So right here, y is 4, and right here, y is 4, and over here, y is 4. So my y equals 4 line is a horizontal line with a slope of 0. So if I looked at this case, the domain, what possible x values do we have? Well, it goes forever in the left and right direction. So the domain is negative infinity to positive infinity. Next, the range. What y values does the graph use? Well, it doesn't happen down here. It happens at 4, and then it quits happening up above it. So the only value in the range is 4. That's the only y value used. Next, where's the graph constant? Well, it's always constant. If I walk from left to right, it's staying the same. It's not increasing or decreasing. So this graph is constant from negative infinity to positive infinity. And then lastly, is this a function? Well, does it pass the vertical line test? Yes, it does. So this would be a function. And then the next one is a graph of a vertical line, x equals negative 3. Okay, so x is negative 3 here, and here's negative 3, negative 1, negative 2, negative 3. And here's the point negative 3, 1, negative 3, 2. So I have a vertical line for x equals negative 3. Now the domain, that's the list of x values. So the graph's not happening over here. It happens at negative 3, and then it doesn't happen over here. So the domain of this function is only at negative 3. The range is the y values. So the graph is happening all the way down here, and it still uses all these y values all the way up. So the range would be from negative infinity to positive infinity. Okay, now where's the graph? Increasing, decreasing, or constant? Okay, well, as I'm walking along, there's nothing happening. And then as soon as I get here, everything happens. So is it increasing? Is it decreasing? Is it constant?
It's undefined.
It's none of those.
You can't.
It's not a function, so we can't really talk about it as increasing, decreasing, or constant. And the reason is it's not a function. It does not pass the vertical line test, because if I drew a vertical line right here, it would touch the graph more than once.
It would touch it infinite times.
Wow. Grape.